You can start at will.
Hello and welcome to our webinar. I'm Pete Starkey, a member of the Council of the Institute of Circuit Technology, which is dedicated to technical aspects of printed circuit board manufacture and assembly. The Institute continues to successfully provide its members with opportunities to improve their knowledge of manufacturing process technologies, materials and practices, and to stay in touch with current and future developments. The future of printed circuit manufacturing and assembly will rely heavily on automation and the establishment of the smart factory. What will this involve, and what additional skills will engineers need to learn? A leading expert in this area is Happy Holden, Honorary Fellow of the ICT, who has kindly offered to deliver a series of 8 one-hour webinars based on his recently published ebook, 24 Essential Skills for Engineers, which is free to download from the iConnect 007 website, and which will form a valuable resource for in-house training of engineers and their career development. In his initial presentation, Automation and the Journey to Your Smart Factory, Happy introduced the elements of the journey and discussed the key issues: who, what, how long, when, and how much. In principle, he advises that you avoid factory automation consultants who will typically charge you for learning your processes and procedures while selling their own equipment and software. Instead, Happy suggests that you select your own engineers who are familiar with your own processes and procedures and let them learn how to do the automation planning. Then they can teach others this essential skill, which the factory will need over and over again. Last week, Happy defined automation and automation methodology. And in today's presentation, the 5th in the series, he examines the realities of the smart factory. If you have any specific questions, please direct them to happy@iconnect007.com. So Happy, over to you.
Thank you, Pete. Let me get my screen up here. And good evening, good afternoon, everyone. This is our 5th in this series. If people are wondering, why the program is centered around the ICT, it's because the ICT, although maybe not known as much as the larger organizations like SMTA or IPC or EIPC, is a very active and knowledgeable group in the focus of technology and other aspects of printed circuit fabrication and assembly. And I've been a member for a long time and value their quarterly journals, technical sessions, presentations, etc., that I encourage everyone to take advantage of. I think some of the free offers they're making for everybody attending this set of webinars, because they have provided a lot of really interesting work, especially their tight connection with the UK university and government-funded programs, which hopefully will add to this program available that people can download. This particular lecture is focused on the smart factory. Last lecture was really on the automation and the methodologies, and the automation methodology. The smart factory comes from chapter 2 in this automation and advanced procedures in PC fabrication. Hopefully you've downloaded this free ebook, because the ebook is more detailed than what I can present in an hour. And so, if you have questions, first thing is see if the ebooks more detail answer those questions. If not, like I said, I'm available at happy@iconnect07.com. Even in the future, if you get around to not actually implementing or starting working on this for a while, but then you can download these recordings and refresh yourself, as well as working with the ebook. Today I'll talk a little bit about IPC 2581, alternative program logic controller communication standards, and then the other 5 standards that are available in factory automation: GM and GE's MAPS, IPC's CFX, Siemens, and then SEMI, and there's SexGem. And then wrap that up with an example in the video on Green Source, which is kind of the world's best example of Industry 4.0 smart factory. But we're really talking here about this extra dimension that I have here, network communication, which is the information. We covered the systemization and mechanization classes, as well as material handling. Those 3 dimensions are pretty obvious in terms of working with printed circuit and assembly. The other dimension will allow you to move from islands to integrated automation. And there are really kind of 5 horses in this piece I'll talk about. The programmable logic controller standards, which are many; General Electric and General Motors development of the MAP standard; IPC's CFX standard, which is 2591; Siemens standard, which is based on ODB++ and OPM; and then the semiconductor industry's SEMI's SexGem standard. So factory communication standards, when you're trying to look at integrating these islands of automation that you've purchased over the years, there is quite a list of how all these different things go. If you look at my shortened list here, you may not be familiar with Profinet or the GEM standard or IPC CFX or the MAP standard or OML or Modbus, but these are all out there currently today. This is one of the dilemmas. While you've got to have kind of a data engineer, usually an electrical engineer, someone as part of your team that's going to work with all of these different methods, if you plan on eventually taking advantage of what's being offered by the Industry 4.0 and others methodologies. There are, like I say, many different programmable logic controllers, PLC, in terms of CAN opened, DMG, net, device net, Modbus, Profibus, OPC. And that's because the programmable logic controller is one of the most cost-effective and ubiquitous machine controller system around today, in terms of both its costs. They typically a controller with analog and digital I/O, starts at $100 or so, or 100 pounds, and then moves up. And so it's all over the industry and around the world in terms of what it has. Now it's developed to the point where it's quite useful. The other standard, which I'll introduce, is the MAP standards, which is message automation and protocol simulation. It was developed by General Motors with the help of General Electric back in 1989. And the MAP standards are quite well developed. You can see a picture here. If you want to get a hold of the Hewlett Packard Journal from August 1990, which is still available on the internet, excellent article in detail. But MAP standards has MAP 1, which is used for NC machine protocol, MAP 2 for simple PLCs, MAP 3 for complex PLCs, and MAP 4, one of the most important, is used for robotic and robotic assembly, material handling. And then MAP 5, 6, and 7 is used for process control, simple, medium, and complex. This made up a lot of our automation focus in the 80s and 90s around larger OEMs around the world. And so this standard has been proven and available, is an open source standard available for anyone to use. But I'll start out with kind of talking about the printed circuit board design data standard, which the IPC has been working on, 2581. And the reason that we start with the data standard on design is because the IPC has been specifically working on this, as you can see down there, under Enterprise Business Systems, ERP or PLM. The 2581 master can be broken out into the fabrication mode of building the bare printed circuit board, or it can be broken out into the assembly mode, which provides the bill of materials and information for automated assembly. So 2581 is a English and language and visible use of the single board, and then how it's going to be panelized and put into either bare board fabrication and test or assembly level and test in routes. And that's very important because the 2581 is specifically integrated with the IPC CFX assembly method. And so, you know, preparing areas of data preparation for manufacturing execution, the digital engineering of selecting materials and analyze it, and then the execution of the manufacturing of that in terms of different digital threads from the IPC, hopefully all seamless and automated. And so 2581 provides an intelligent handoff, either to go to the fabrication area for all of the files and information to actually build the bare printed circuit board, and then for assembly, providing the digital engineering information for placement, testers, AOI, and also hopefully the box build. Again, this is from the 2019 SMCA eSmart Factory presentation IPC made. So the 2591, which is the IPC Connected Factory Exchange, is CFX, Connected Factory Exchange. It's a free and open source industry standard focused on Internet of Things plug and play capability. It's consensus based, working with 300 different participating companies in developing the IPC standard and software for machines, processes, systems, and even humans. There's no licensing or contractor dependencies, and it's for all discrete assembly manufacturing, first published in April 2019, and constantly updated by the IPC for everyone's use. It uses a communication protocol that's very secure, like ATMs for banking, the AMQP, and it has a defined language content with structured topics and messages about printed circuit fabrication and assembly, and the data encoding using a JSON methodology for the the components of the CFX. It's basically, based on messages and communications bidirectionally, in terms of downloading recipes, work orders, various other information that is useful in electronic assembly, and uploading that information and then providing communication machine to machine as the particular printed circuit board goes through the assembly process with that. And it's kind of a driver for Industry 4.0 in terms of it's by far the newest connected factory communication exchange, but also today one of the most robust and fastest developed because of the enormous contributions companies all over the world have made to help develop this, so that the entire line solution in terms of solder paste printing, AOI, reflow, testing, even manual insertion, repair and assembly, all the way out to shipping, it is made available, hopefully, to a plug and play connectivity that in many ways eliminates a lot of the work that you would find very difficult and exhausting to do. But it also provides the opportunity for companies to develop smart software that they can sell, to provide other even more significant results in terms of closed feedback loops that were not closed in the past, from paste inspection now being able to do corrections back in real time to the screen printer, or paste inspection, changing some of the SMT placement and areas like that. For some of the recorded results is decreasing first pass failures, by a factor of 10, decreasing the average cycle time, and increasing product reliability. And this can be provided anywhere with that. CFX also provides assistance in that the CSX has SDK development information available to users for the first time and to machine developers, so that it is implemented in their machine in the consistency and focused methodology that needs this to be plug and play, where you don't have to worry about that as long as it's CFX compliant. Just plug it in, and these messages will be passed back and forth or in and out to the humans, everything like that. So it's a very, very involved program that has a lot of users. The overall SMT architecture includes also smart tools, human inspection and rework, and beginning of the addition of co-robot material handling, as well as static monitoring process and environmental humidity and temperature monitoring, as well as the standard pieces of equipment, is illustrated here: screen printer, solder paste inspection, pick and place, automatic optical inspection, and reflow oven and conveyors. And in the past Apex meetings, they've actually assembled these equipment and demonstrated the CFX in real time for people. So the CFX is a digitization for the smart factory, but one of which, hopefully, because of 2581, includes the design engineering into the program, as well as the component engineer and the selection of materials, and then procurement, as well as suppliers of material and components and equipment, and then the manufacturing in terms of assembly and test plans and build schedules, tooling fixtures, et cetera, in order to make this uh, um, a smart factory implementation. Currently, the reason 2581 has been so successful is it started out with 100 corporate members, starting in January 2016, but since January of 2019, they now have over 300 corporate members. Here are just, some of the corporate members that you can see there, but the ability of everybody working together to come up with a mutually agreed upon methodology, as well as the communication software and messages that go in and out. And as people join it and add new capabilities or new technology, then they also submit the requirements for new messages, maybe for their technology that currently doesn't exist. And that goes through this corporate and committee organization quickly to be approved and then set up again as the standard revision of the software to provide for technologies and enhancements. Now, it doesn't leave most of us out because a number of people, have equipment that is not CFX compliant and perfectly modern equipment. It just doesn't have that communication standard. Well, fortunately, Seika in Italy has used the popular Raspberry Pi computer that you see up there on the right with their own data acquisition system that plugs into the 40-pin GPIO of the Raspberry Pi to provide a box that they call the Seika shoebox that provides both monitoring for sensors and equipment that is not, it's intelligent, but it's not CFX integrated, and maybe the future models will be CX, but the models that you have are not. This allows, through the use of this box, to bring older non-industry 4.0 equipment into this organization. And the interesting thing about this one is that it uses and makes available radio as well as power line communication within the factory. And then their master, provides the connectivity up to the cloud or manufacturing management software, things like that. So this, provides a way that you can tie in the entire production line, even if the equipment is not CFX compliant currently. A fourth one was developed by Mentor and now Siemens, based on the ODB++ thing. And it starts with the OML. And OML is an adaptation of the Semiconductor Integration Initiative, developed actually by TSMC in Taiwan, called the TSMC Model Interface, TMI. And this was voted by the Semiconductor Consortium. The new model is an open model interface, still pending as a semi-standard. But this one utilizes different levels of the ODB++ design information to provide for DFM handout, process engineering, assembly production, and assembly box build. Siemens has, as part of this, developed specific hardware that you can see there on the right that are data floor data collections in terms of master unit and individual units. And this provides the connectivity with their software to move information up and down in the hierarchy of the factory floor in terms of recipes, similar to CFX, things like that. In terms of theirs, they have various Siemens software available at each level of the cloud, enterprise, MES level, as well as the factory floor level, using their OML data exchange and their data collection boxes that connect this part together. So the Siemens one, based on their acquisition of Mentor and everything like that, is focused on capturing raw data and then moving that up and interpreting it and then normalizing the data, then adding perspective mixed with other data to qualify the data in terms of this control or not, and then distribute the data and use the data to integrate it with the computerization in terms of MES and ERP software to provide the smart factory connectivity, utilizing their line controllers and gateways, hardware boxes provided. A little bit different than the CFX, which is putting this within the controllers of the equipment themselves through the CFX software. So the Siemens one, if you look at their advertising, it focuses a lot on digital twin production simulation. And so that, they talk about digital twin of the product, the virtual product, digital twin of virtual production, and focusing on real production automation and real products as a collaborative platform. The last one is the most complete and the largest of one. The fifth one is from SEMI. And SEMI, the Semiconductor Consortium, developed in the early 80s the hardware and software to connect wafer fabrication up and down the computerization line for remote control of equipment and online and monitoring and remote diagnostics, as well as equipment simulation. The parentheses there, IC10, PC10, E5, E4, E31, these are actual software products that I used to consult on at Hewlett-Packard sold in order to make this automation hierarchy work. But this was established in the mid-1980s for every semiconductor manufacturer around the world. And so the SEMI 6Gem standard, is again based on standardized method and standardized drivers and interfaces to specific pieces of equipment, then provide both recipe and input of data, control of processes, and then upload and download of recipes to other factory level systems. But it has an enormous installed base because first being adopted by the semiconductor people around the world, as well as by Hewlett-Packard and others. It then got adopted by the photovoltaic manufacturers around the world, and then adopted by the liquid crystal display, LCD manufacturers around the world. So because of their longevity and being an open standard, it's been growing more and more. And interesting enough, the reason I say it's a fifth horse is SEMI has now decided to move this standard down into the box build and board stuffing assembly level and down to the bare PCB fabrication as a standard to compete with other standards that may be out there. And in fact, an example of this is Atotech. Atotech that manufactures very complex automated equipment in printed circuit fabrication and in photovoltaic and LCD manufacturing. They're communication standard and interface is either OPC, popular in Europe as a programmable controller standard, as well as providing also SECGEMS standard in terms of their communication interfaces, so that Aditech equipment can interface and talk with non-Aditech equipment, such as a loader or unloader of their equipment that they may not have supplied. So this standardization ensures compatibility with process equipment, and that the process data is being captured in real time and provided to where it may be needed for decision. And that provides decision makers the meaningful information, as well as initiating based on continuous flow of data to improve quality control, paperless workflow, and product panel customization. Again, no need for manual parameter settings being involved. The interesting thing is that SEMI has focused on and allocated to the Taiwan Printed Circuit Association, TPCA, the requirements to work on the SEMI standard for bare PC fab protocol standard. And this is a translation from the Chinese, from the TPCA actually, in terms of their project, put together this SCCS and GEM gateway down into specific equipment for exposure, drilling, routing, etching, plating, conveyors, baking, different parts like that. And they plan on implementing this in 20 medium-sized factories in Taiwan as part of the TPCA program, as they test out this new standard and the device networking verification and online visual verification as the SEMI standard that will be voted on by SEMI, in the same way that SEMI developed the semiconductor protocol in terms of the world's semiconductor manufacturing in virtual lights out factory is implemented all with these SEMI standards. And the nice thing about semiconductor fabrication is, in many ways, it's parallel to printed circuit fabrication and other hybrids, in that instead of the wafer, we've got the panel, and instead of the die, we've got the board. But these are all different types of processes. They are not assemblies in terms of a bill of material that's collected together. These are thermodynamic processes that are yield sensitive and in many ways non-reversible. Now, there are going to be also numerous factory proprietary standards, this one being from Panasonic, you can see there, available. And there'll probably always continue to be companies that utilize their, their presence in order to put together a custom solution. The interesting thing about the Panasonic one is that the Panasonic one also accepts the SEX2 GEM standard from SEMI, which is interesting, as although theirs is proprietary, there's a compatibility with the SEMI standard in assembly. So, how does this kind of horse race finish? Well, I don't know. They may all finish. Being too close to call a winner. My own personal opinion is that what we're going to see is something like IPC 2581 growing as a standard and defining the product, with the DFM handoff from 2581. And for assembly, it goes to the IPC CFX for assembly and test. For PC fabrication, it's likely to be this SEMI's GEM, SEX GEM standard for PC fabrication. And then for box build and robotic assembly, either the OML or the GE General Motors MAP standard may be there. So the entire sequence, is likely not to be one particular industry standard, but a group of open source standards that we've talked about here, which unfortunately, makes it a little more complex, but nonetheless, everybody's coming from a different direction with that. So the Industry 4.0, the smart factory we're talking about today, it's focused particularly on, sensing in terms of real-time processes and data, connecting these different unique data sources, and then predicting the outcome, with a digital twin. Prediction is a unique focus of Industry 4.0, but to date, I've not seen any examples of software available that offer much such predictions other than semiconductor digital twins that came about 30 years ago as simulation. As my part of working with Hewlett-Packard since the 1980s, what I call the Industry 3.75, it's not Industry 4.0, I and my team developed 3 different digital twin standards 30 years ago. A very accurate yield prediction model for PC fabrication based on design parameters that had a first pass yield error of only plus or minus 3%. The second thing, we developed a performance simulation of a virtual PC board, in other words, software digital twin, that allowed us to test materials and design rules and placement and routing before we physically got into a CAD system and designed the PC board in order to optimize that design. And then lastly, with the help of HP Laboratories, we developed an automated printed circuit design system using a self-learning artificial intelligence that would design a complex multi-layer, high-speed, etc. Instead of in 4 to 10 weeks, would do it in 4 to 10 hours. And in all cases, though, the system that was developed, the artificial intelligence designed a superior printed circuit board with higher yields in manufacturing, higher reliability, and lower cost. Unfortunately, none of the EDA companies were interested in what we had invented, and that technology still sits on the shelf. One of the reasons we were able to develop these digital twins is based on a lot of the elements that we're talking about here in this series of 8 lectures. And there's 3 areas of focus, control series in terms of sensors, and we'll talk specifically more about that on the next lecture. The design of experiments, which provides prediction equations and models, and the figure of merit predictions, which we'll get into in the last lecture of this series. So, the predictive solutions for smart factories, one of the ones that keeps coming in over and over again is the maintenance example. Talking about traditional method of reactive maintenance and preventive maintenance, product testing, manual inspection, etc. And then the smart factory one, which is that of predictive maintenance or predictive quality or predictive process monitoring, with the benefits being on the smart factory, reduced unplanned downtime, improved uptime, increased productivity, minimizing of spare parts, improvement of product quality, reduction of scrap, reduction of inspection and testing costs, and reduced waste product line time, as well as improving product quality, reducing scrap, and detecting process drifts during bad parts are produced. This whole area of predictive maintenance one is based on this predictive analytics, which is transformational as part of the 4.0 in terms of again, in maintenance, moving from reactive maintenance, where you fix things that fail in firefighting, to one of preventive maintenance, to one of conditional-based maintenance, and finally one of prognostic and health management, PHM. The PHM is a system discipline focused on detecting, prediction, and management of the health and status of complex engineering systems. And in this case, if we're dealing with a more and more automated networked manufacturing operation, then this constant doing predictive maintenance and prediction of that is an essential part, because you fundamentally can't afford anything to fail, under this kind of methodology. Though one of the ones, that people that sell the 6-gem software messaging system talk about the gigafab, and these semi-standards are used worldwide for photovoltaic, LCB, and increasingly PCB fab, again, for almost 40 years now. This is just a snapshot of the semi-gem standard used around the world, and has been for, again, the last 20 and 30 years. Other typical smart factory architectures of factory setup and control systems and factory analysis and execution systems we've mentioned before. And this is available in more detail in the third 007 free ebook that you can download, that will go into manufacturing execution systems and the advantage of that type of software in your smart factory, as well as 5G enabled smart factory scenarios in which more and more will be wireless. And because of that, again, you don't have to necessarily, run cable over the factory. That a lot of this, one reason why the Raspberry Pi is used, because Raspberry Pi comes integrated with the wireless Wi-Fi networks, as part of that $42 computer system. As an example of this, I'll come back again to Whelen Engineering, but this time Whelen Engineering in 2018, in which they were so successful with their 2015 pilot plant, they did a 5 times expansion and created a merchant called Green Source Fabrication. Some of the equipment pictures here. Here's the layout of it. You can see this in many of the printed PCB 07 magazine. One of the reasons why is that it's a lights out factory. So, here's an actual photograph of the Green Source multi-layer fabrication facility before they turned the lights on, so that we could run our drone down and photograph it for you with that. And so different direct metallization and MSAP electrolysis processes, a new generation of through-hole and blind via plating that provides up to 5-to-1 blind via ratios and up to 30 to 40-to-1 through-hole aspect ratio. And then the through-hole and blind via panel plating, and as well as, again, part of their direct metallization, SAP, and surface preparation systems. The lamination utilizing the new induction two-sided automatic laser drilling, inline electrical test, inline hole plugging, X-ray, plasma desmear, and drilling and imaging. Their imaging, this is a semiconductor one, is down to 4-micron traces and spaces. But part of their Industry 4.0 example is one, and that is an illustration, an excellent illustration, Industry 4.0, in which you measure, the data in real time, learn from it, and then use that to predict. So, leading to predictive data and prescribed actions against, for hindsight, insight, and foresight in terms of the data analysis. So, this is an excellent example of utilizing sensor data and equipment data to actually improve the quality and productivity of plating and electrical test and exposure in real time. And so, again, this new green source facility really has only 19 technicians for 24/7, but they're still recruiting engineering. Zero effluent. Again, even though it did a 5-fold expansion, they actually use less water. The water being used is less than the actual toilets and community water usage, as well as the chemical recycling. And the copper recovery now is an even greater profit center, paying for a lot of that because they're etching up to 6-ounce copper, and all that copper being etched is recovered as copper itself to be added back. Moving on to induction lamination that saves them enormous amount of energy and costs, as well as providing the temperature to handle flex rigid and other types of materials. 3 different SAP processes for HDI. Again, 2-sided laser drilling, significant hole filling thing. 3 different metallizations, 5 different copper platings for blind hole copper plating of either high throw and or copper filling or blind via, and the ability to intersperse multi-layers from 0.4 millimeters up to 8 millimeters thick simultaneously in production. So with that, I'll run this quick overview for this. Get out of this mode. So, these videos really are useful for benchmarking. Although this is a totally greenfield site, built from the thing up, from a benchmarking point of view, Wheeling has demonstrated that 100% of water can be recycled, and it's simple and practical. Wheeling has demonstrated that all PCB fab processes can be automated and operated without human operators. And they demonstrated that metal recovery from copper etching can produce profits. And they've demonstrated that automation in the smart factory is a competitive advantage in this industry. So depending on what each of your plans are for the future in the next 5 years, this is an excellent benchmarking Again, because several videos are included in the 9 articles about Wheeling and Green Source from iConnect 007 from 2015 to 22. And there are 6 additional videos available on LinkedIn if you go to LinkedIn about Green Source Fab. From these videos and the articles, you can then collect data about, what is capable in terms of technology, and should that be your future goal or not in terms of, zero operators for this particular process, or greater productivity, or the ability to mix products together with it. The greenfield and the green source fabrication is probably the most advanced printed circuit fab in the world, capable, like I say, of up to 36 layers, sequentially laminated, or any types of thicknesses, and line width and geometries down to 4 microns, with extremely high yield, controlled impedance of plus or minus 2% on that. All of the, again, emphasizing that this is the technology that has been developed and can be used, and then used in your research, to go forward with that. And with that, thank you for your attendance today. I'll see you next week. And like I said, any questions, you can email me at happy@interconnect07. But be sure and read the ebooks or articles first. If you send me a question, again, because what I've only spent an hour on in summarizing is in much more details in the material I've asked you to download. With that, thank you for your time and attending today.